Okay, for this activity, I'm going to talk you through, we're going to use different types of earthquake waves. We'll be talking about primary and secondary waves. We'll try to make sense of what's taking place within the Earth's interior. So this is for lab exercise 6. You're going to conduct various lab activities and solve the math in order to learn the following concepts. We're going to learn how to use primary and secondary waves to define the different layers within the Earth. We're going to be able to determine the depths of different boundaries. So we're going to use these waves to be able to make a lot of deductions and draw some conclusions as to how the interior Earth is structured. So here goes. First off, we need to make sure we understand what a longitudinal wave is, which we're going to call a primary wave. It's simply saying that the wave propagation or direction is in the same direction as the particle motion. That means an oscillation is going to be in the same direction. It's going to be left and right as the wave travels from left to right. So we define that as a primary wave. Whereas a transverse wave, if a wave is traveling through me, I'm going to move up and down as the wave travels from left to right. So this is simply defining the wave propagation or direction is perpendicular to the particle motion. We're going to use the primary and secondary waves. These are body waves. These are what travel through the Earth. These are going to be the types of waves, the primary and secondary waves. These are what we need to make sure we understand what's happening here. So let's watch this video to further that.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
So once we understand that primary and secondary waves can travel through the Earth, we simply are going to be looking at these waves that travel through the Earth. We're going to call them body waves. And we can actually start making sense as to the depths of the layers of the Earth because they're going to reflect back. So therefore, we can use primary and secondary waves to get really essentially a view of what is taking place within the Earth without being able to see it directly. Or instead, we're going to use waves to make sense of it. So let's watch this animation. This simulation shows the motion of P and S waves generated by a single earthquake. Notice up here at this green point. The waves spread through the planet in a series of expanding spheres. Some of the wave energy is reflected off the boundaries between the mantle and the core, technically between all boundaries. Scientists deduce that the structure in the Earth's interior and how waves move through it by analyzing thousands of earthquakes recorded at the Earth's surface. Examine how the waves change as they encounter different layers of the Earth's interior. Identify areas on the surface that do not receive any waves. These areas are in the shadow zone of this simulated earthquake. If I look at the dark blue and the light blue, I can see that different waves are able to be transmitted through, which is my primary waves can travel through solids and liquids, whereas my secondary waves, which are in light blue, are not able to transmit through a liquid layer. So therefore, the liquid outer core is simply the result of the conditions here. We know it exists because the S wave, the secondary wave, cannot travel through it. So it has a much larger shadow zone. So now, we can put together the use of the primary and secondary wave features and start making sense of what is taking place within the Earth's interior. And we know this from seismic waves. So viewing the inside of the Earth is possible due to seismic waves. There's a tremendous amount of information we can determine by understanding seismic waves. And lastly, if you look in your binder, we can actually do the calculations and determine, well, how deep are these layers based on when they reflect back to the surface. So based on the provided data, you're going to draw and solve for the depth of a boundary, and the answer key is explained on this video. An earthquake occurs 530 miles from a recording station. The earthquake occurred at 10 p.m. The primary wave, or the first primary wave arrived at 10:01:09 p.m. The second primary wave that reflected off of the boundary arrived at 10:01:14 p.m. You may assume that the wave speed was constant as it reflected through the crust. Here's a drawing that'll coincide what is written here, and here is where I will show you how to solve it, and I'll walk you through it.